So next up we have Angelos Tsiaras, who will tell us about PyLightcurve, which is package for modeling light curves of transiting exoplanets.
Thank you very much, Sally, and good afternoon, all. Thank you very much for the opportunity to present my Python package called PyLightcurve, which is dedicated to modeling transits of exoplanets. All right, so you can find PyLightcurve on GitHub. It's written completely in Python, and the main purpose is to model transit light curves, but also it offers the opportunity of having a toolbox in your computer about exoplanet light curves and calculations. So it is also useful for other stuff, not just for modeling of light curves. And here is the link. Now, the main functionality of PyLightcurve, as the name says, is to calculate the light curve model, which mainly for exoplanets is the transit model. So we have a star here, and if we think of the star as having a radially symmetric profile, so it's not including any sophisticated models for the atmosphere of the planet, it's a simple radially symmetric model. And then you have the planet coming in, that's all. And all you need to do to calculate the transit model is to integrate your stellar flux over the area of the planet. Now, the stellar flux can be described with different models. And the main reason I kept actually PyLightcurve started being, not with this name, but started being developed many years ago. The reason I kept developing it and using it is because I want mainly to focus on using the four coefficient law. This is quite common in the exoplanet community, using the four coefficients and named as Clary. And the reason for going for this is because it's more accurate, obviously using more coefficients for the profile. However, it has a drawback that it's more computationally expensive. I also would like to work on Python. So on this route to solve these integrals in PyLightcurve, all this the integral about the whole light curve and is written in just one equation. And I will not bother you too much with equations, so I will highlight this one. I have to say that these are not really described in a paper, so I'm writing this paper. I have written this paper now and will submit it within the next few days. I was hoping to have it today, but it's not there. Anyway, so the point is to have everything written in one equation, and in this way, this can be vectorized in Python. And for Python, this is a very important thing because it is the best way to proceed with calculations. In the new version that will be available soon, there is also a hack to calculate these integrals a little bit more accurately. So if you are doing a light curve modeling, this may be helpful as well, is integrating actually over the 99% of your integral and then a small 1% at the end separately. And this is because the integration at the edges is the one causing the errors usually. So with this hack in mind, I would say that the strength of PyLightcurve is using only Python. So if you don't want to have any wrappers around other languages, you can focus on this. It's fully vectorized, so it's optimizing speed and scalability, and also gives precise calculation for the four coefficients law integrals. Talking about precision, of course, you cannot really compare this without numerical codes. So here I present a comparison between a transit model calculation between PyLightcurve and Batman, another package developed by Laura Kreitberg, which does this analytically. So in this comparison, we can have a better idea of the error. So with these calculations, we can go down to error of a couple of parts per billion. So this is like very small, and for the large majority of the applications we are running in Exoplanet, this is sufficient enough. Now to a level where I'm not sure where at the moment these errors are coming from, whether it's from the numerical integration or the analytical. But anyway, point is that the errors in the model are negligible, and this is what you want when you try to fit precise light curves. Another precision is a thing that is changing with the size of the planet. So for larger planets, unfortunately, we have more error. Let me see a slide. So the maximum error is, as you can see, with the blood curve, which is the default value. So precision of 2, I forgot to mention, means using 20 quadrature points for the integral. 10 means using 100. And you can see, however, that for most of the applications of what we say normal or common planets that have an RP over R star of 0 up to 0.2, the maximum errors are for the transit below 0.02 here, and for eclipses even lower. Now coming to speed, I know Python cannot really compete, pure Python cannot compete with C in the calculation or Fortran, but however, in the way that is written, and if you follow completely Python, then the way that PyLightcurve implements the model makes it scale up in a good way. So you can see here that as we increase from 10 data points in the light curve to 10,000, the increase is not 100. So this offers the possibility to do larger arrays without linearly increasing the execution time. Also, the way PyLightcurve is written, it can be applied with machine learning applications. In fact, a colleague of mine, Mario Morvan, developed a few years ago a package which is based on PyLightcurve, and it's called PyLightcurve Torch. It is written in PyTorch, and it gives GPU compatibility, and also can be used in deep learning applications. You can also see that here, scaling up with time using CUDA, it can help you run large batches of light curves without increasing and without almost with stable execution time. Now, PyLightcurve also offers links to other databases and tools. So apart from calculating the transit model, as I said, I would like to provide an environment where you can have all the basic important calculations related to a planet in one place. So it is connected with a database from the Exoclock project, which is a project to monitor the targets of the potential targets for the Ariel mission. And through the Exoclock project, we have prepared a list of planets with verified parameters and ephemerides and stellar parameters. So you can have direct access to these parameters just by typing this small piece of code. And also through the planet and by using the ExoTithis package, was developed by another colleague, Giuseppe Morello. It gives you the opportunity to calculate limb darkening coefficients for different laws, and also for different filters or sub-filters. So it will be useful for your applications. You can also calculate quickly transit depth, duration, and same for eclipse, also produce time transformations. Within this framework, what actually is the important thing from my perspective is to be able to analyze many different light curves together and quite easy. So PyLightcurve takes care of all the transformations that needs to be done. You can throw at the planet object literally different observations from different instruments for the same planet, of course, and then the code will take into account any time conversions, flux conversions, will calculate the limb darkening coefficients based on the passband of each instrument, and then it can apply fitting of the transit depth or eclipse depth and time by keeping fixed all the orbital parameters and also applying different systematics for its observation. And also the recent version, there is also the option of applying custom detrending for the systematics of its instrument. So I will close this short presentation by some light curves that where pi-lightcurve has been used, starting from James Webb and the WASP-39 ERS NIRIS observation that was analyzed here. Then the HST here with the peculiar systematics that HST has. Then Spitzer with these time variations that are related to the position of the star, and also small telescope where you can have air mass trends usually. So by being able to easily change the detrending function, you can actually switch between instruments and being more confident when having results from for different observations and different data sets. Just to mention also that in the end, it gives you, of course, all the nice plot that you want and diagnostics based on the residuals on whether your fitting was successful enough and whether there are any residuals or any outliers in the data. Yes, that's it. I don't think I have much time for more, so thank you.
Thank you very much. Please go ahead and either you can raise your hand in the meeting, or you can post questions in the Discuss Talks channel of Slack if you would like to ask a question. And I'm looking at that. I think you said it was Spitzer-Lightcurve on the upper right-hand side of this.
Yes, it is.
Yeah. So I mean, I can definitely see that there's a lot of variation across the light curve when the star or when the planet is not in transit. But if I were to ignore that part of the plot and just focus on the transit, I might look at that and think, oh, the planet transited a star spot.
Yes,
And
okay.
yeah, so I'm just wondering if that actually happens.
No,
Can you
no, in this one, no. So in this way, you can correlate the flux variations to any kind of other auxiliary data that you have. And in this case, you can actually write yourself the trending model. In this case, is a combination of the X and Y position of the star. So the star is moving on the pixel and you get variations. It's a known problem with Spitzer.
Yeah, okay.
But Sally, you are right. It does happen, as in you do occasionally see star spot
Yes, of
crossings
course.
in transits. And it is a big challenge if you're trying to decorrelate and you don't have all of the data that Angelos is talking about to figure, to differentiate. So it is an issue.
Yeah.
Of course, it can happen. It's just not here.
I think I might remember actually when the very first planet transiting a star spot was seen, and it was kind of a cool thing, and some people were saying, "Oh, maybe that's a double transit," which, would have been really awesome.
That was
Um,
me, actually. Do you know?
really?
I was convinced it was a planet event, but they were not. I was a student back then.
Yeah, I was too. It was just fun to speculate about. That's pretty cool. All right,
And you
thank
remind
you.
me actually that the first reason I wrote the package was to be able to model planet-planet occultations. I still have the code from 10 years ago, but I have not. I will publish it at some point as part of PyLightcurve. But in the way that the integrals were solved, this can be done.
Yeah, I mean, I know that you wouldn't necessarily want to put a lot of work into something that you don't think is gonna analyze a lot of systems, but I bet students would love that. I mean, that would be so fantastic for, master systems to play with and just say like, hey, what happens if you do have a double transit, or what happens if you do this or that? So I could see that being a really good educational tool.
There are indeed one or two events in the whole Kepler catalog that can give you the mutual inclination of planets.
Okay, cool. All right, well, thank you.